Hi everyone, my name is Newton and I'm here with another Leetcode practice video. Today's video will be Koko eating bananas. So let's get into the problem. First, we're given an integer array piles, where piles I is the number of bananas in the ith pile. I'm also given an integer h, which represents the number of hours that I have to eat all the bananas. I need to decide a bananas per hour eating rate of k, and each hour I can choose a pile of bananas and eat k bananas from that pile. If the pile is less than k bananas, I can finish eating the pile, but I cannot eat from another pile in that same hour. I want to return the minimum number integer k such that I can eat all of the bananas in piles within h hours. So first things first, let's keep track of the input, jot down the input and output, make sure I understand what's being asked. So the input is an integer array called piles, where each pile is a number that represents the bananas in that pile. The second input we get is an int called h, representing the number of hours we have to finish all piles. The output is an int called k, which represents the bananas per hour eating rate. And something I want to note here is that we're looking to minimize this number. We want to only return the smallest value of k that meets this requirement of being able to finish all the piles. So there are a few questions that I would have about this problem, and I want to see if the context, the constraints, can give me some answers. So first things first, let's take a look at what we have. The first constraint is that the number of piles is between 1 and 1,000. Some important things that this tells us is that there can't be 0 piles, and there can't be some edge case where there are a negative number of piles somehow. The second the second constraint that we get is that the piles of length is always less than or equal to the number of hours, and both are always less than or equal to 1 million. This tells me that there won't be a situation where we'll have 4 different piles and only 3 hours to finish all 4 piles. One of the rules that we got before was that we can finish a pile, we're free to finish eating from a pile, but we can't eat from another pile in the same hour, and that rule tells us that we must spend at least 1 hour on each pile. So this information, these rules, tell us that we will have enough time to finish all piles. And I'd like to actually write that as a rule too. The rule being, of course, that we must spend minimum 1 hour per pile. We can't eat from more than 1 pile in the same hour. Now let's get into the third constraint. Each pile has at least 1 banana, and at most 1 billion bananas. This tells us that there won't be any, we won't have to worry about empty piles. So with that said, let's take a look at some edge cases and some examples. And let's take a look at some examples first. Let's take the first example where the input is a group of piles, 1, 4, 3, and 2, and that we have 9 hours to finish all of these piles. So the output, the answer in this situation, is 2. And why is that? So we can eat the bananas with an eating rate of 1. We would need 10 hours to finish all the bananas. We would take 1 hour on the first pile, 4 on the second, 3 on the third, and 2 on the last one. And that would total up to 10 hours, which is not enough time to finish all, which is not enough time. So the next next value k that we can choose is 2. And if we test it, it'll take 1 hour to finish the first pile, 2 hours to finish the next, another 2 hours to finish the next, and then 1 hour to finish the last pile, which totals up to 6 hours. We know that 2 already works, and since we're looking to minimize the number k, there's no need to look at any other numbers once we've found 2. Let's take a look at another example. In this one, we have 4 piles, 25, 10, 23, and 4. And we have 4 hours to finish these 4 piles. So going back to one of our previous rules, we can't eat from more than 1 pile in the same hour. So that means we can't use 1 hour to finish multiple piles. We need to spend a minimum of 1 hour per pile, and with the time constraint of 4 hours, that means we will have to spend exactly 1 hour for each pile. So what does this mean? We need to have a k that's high enough so that it can finish all four piles, but not greater than necessary. So what will that number be? K can't change between the different piles, so we need to guarantee that K can finish any pile in piles. So for this one, let's choose the largest number in the piles. This would guarantee that we will spend 1 hour on each of the 4 piles without having to spend more than 1 hour. Whereas if we chose any number that was smaller, say 24, we would spend 2 hours on the first one, and then 1 hour on each of the other 3 piles, and that would total up to 5 hours. So 24 does not work, 25 does work, and any number larger than 25 does not need to be considered here, as any number larger than 25 is completely unnecessary. 25 in this situation is the maximum number in piles. There's never any reason to go above this, as going above does not grant any benefits. Now, when it comes to edge cases, I would definitely consider like empty piles, but from the constraints, we can safely rule these out. Same thing for like if we receive no piles. We also don't need to consider this. We're also given it's also given that we will have enough time to finish all the piles, so we also don't need to consider an edge case where we can't finish. And with that, I believe we have enough information to start considering algorithms that we can use to solve this problem. So first, let's take a look at the brute force approach for this problem. Let's say we want to start with the first example, and we want to start with k equals 1. Then we want to go and we want to check if k works, and then if k works, then we return it, because we know that it's the smallest number, it's the first value of k that works, so we know it's the smallest, and we can return it. And if k does not work, we can instead increment it and try again. So if we started with k equals 1, 1 would not work for the first example. We can increment it to 2, and now we can see that 2 works, and we can return it. This works with only 2 guesses on on this example. However, this approach is a lot less efficient than what we are looking for this problem. The time complexity of this appears to be O of n times m, where n refers to the number of piles, and m refers to the maximum number in a pile. This is because in the worst case scenario with this approach, we could be searching from any number between 1 and the largest pile in piles. Where, we can take a look at the second example here. If we tried this approach on the second example, every value between 1 and 24 would fail, and it would take us 25 different guesses of k in order to get our answer. This approach is too inefficient and and is simply multiplying the number of piles with the maximum piles. Oh, another thing, and why would this, where's the n coming from? So our algorithm to check if k would work, we would need to run through the pile of bananas with k. In order to check if k works, we need to iterate through the piles with our rate, and then compare our hours to h. And this loop would take O of n time complexity, as it's linear to the number of piles that we have. So with this said, let's take a look at the second algorithm, binary search. The reason why binary search can be considered here is because of how we can consider possible values of k. Let's go back to the second example here. If we tried the first approach, we would be trying every value from 1 to 25, or 1 to the max number of piles. And in this range of numbers of possible values of k, we would know that there's a certain point that when you find the minimum k that works, every k that's bigger will also work. And And for each value of k that does not work, for each value of k that doesn't work, we know that every smaller value will also not work. We don't gain anything from choosing a smaller number of bananas, so if we know that one value of k does not work, we can safely disregard every smaller value. So how can we use binary search for this problem? Let's start with k equals, let's say, 1 plus maximum piles, and then divided by 2. Oh, and of course, before we can even start with that, we would need to keep track of a left and right boundary. Okay, to use now we want to check the middle. If k works, we want to track this value of k. We know that this k value works, but we don't know if it's the smallest, so we want to track it, but we want to keep searching as well. This value of k. And once we know that k works, we know that this value and every other value bigger than it can be disregarded. So let's set right to become this value of k, but minus 1, as that's our new boundary. If k does not work, then what we want to do, we don't need to track this value of k because it did not work. Instead, we just want to increment the left boundary now. Now, this time approach should become, it would still be O of n, but this time it would be multiplied by log of m. We're no longer using m linearly. The binary search function cuts in half the number, like half of the digits leading up to piles for each iteration. So we now have a more efficient time approach than the first algorithm without creating any extra space. Even though we're treating possible k values as a range, we're not creating any separate space, any separate data structures or variables that would take up space. So the space would still be O of 1, just as it would be in the brute force approach. With that said, we can begin writing code. So let's implement the binary search. Let's have left and right become 1 and the max of piles. Let's have k start off as the maximum number of piles, because we know that k must be a valid number. And now let's run our binary search. So while left is smaller than right, or equal, we want to take the middle, set it to be left and right divided by 2, and then we want to, if k works, okay. Let's say number of hours will be equal to 0. And then in order to calculate the number of hours for this rate of k, let's search through piles, and then we want to increment number of hours by the number of hours it took to finish each pile. So it should be the pile divided by the rate, but rounded up as we can't have a even if it would take like half an hour or something to finish the number of piles with our eating rate, we can't use that extra time for anything else. So we can just use the math ceiling function to make sure that this number rounds up. Now, this function here just checks, that just calculates the number of hours. In order to check if k works, we want to compare number of hours to h. So if h is greater than or equal to the number of hours, then we know that it worked. We want to set k to the middle rate, and we want to set right to the middle minus 1. If it did not work, then we just want to set left to the middle plus 1. This will continue until left is greater than right, and at that point we can return the smallest value that we retrieved for k. Okay, let's take a look at how this works against our test cases. It succeeded, and now let's try submitting it. Awesome. Okay, so we were able to figure out a binary search approach for solving this problem to return the minimum bananas per hour eating rate that would finish a given number of piles and within a given number of hours. Alright, thank you very much for watching. I'll see you in the next one.